The Internet has been described as the nervous system of our modern civilization. It connects continents, economies, governments, and individuals in ways that just a century ago would have seemed like sorcery. With a click of a button, we can transmit images across the globe, send money in seconds, share knowledge with billions, and even simulate entire worlds. For decades, it has been the beating heart of globalization, innovation, and communication. Yet, as powerful as this network is, it is not limitless. Beneath its astonishing capabilities lie deep constraints, technical, structural, and even philosophical, that form the foundation for why a new evolution, the quantum internet, is not just desirable but inevitable. To understand these limits, one must first recall the origins of the internet. It was born not as the omnipresent digital landscape we know today, but as a fragile military experiment. The original ARPANET of the late 1960s and early 1970s was built to link a few universities and research centers using simple packets, wishing to send digital messages. Back then, speed meant kilobits per second, and the idea of streaming movies, running businesses, or connecting billions of people was inconceivable. Over time, technology leaped forward, cables became faster, processors more efficient, and wireless towers rose like forests across the earth. Yet, even as the infrastructure expanded, the fundamental basis of how the internet functions, through binary signals of classical physics, remained the same. Every email you send, every message, every video call, is ultimately translated into streams of ones and zeros, electrical pulses in copper wires, light pulses in fiber optic cables, or radio waves through the air. These classical signals travel close to the speed of light, but never faster. They must move step by step through routers, servers, satellites, and repeaters, and with each step comes delay, noise, and vulnerability. The very structure of this web is finite, constrained by the speed and fragility of classical information. We live in an age of dazzling connectivity, but behind the glittering screen lies a constant struggle with bottlenecks. The more data humanity generates, the harder it becomes to push it all through the narrow pipelines of our networks, streaming high-resolution video, running massive online games, powering billions of devices. All of this taxes an internet that was never designed for such vastness. Beyond speed and capacity, the most glaring limitation of the classical internet is security. Every password, every bank transaction, every confidential message is protected by cryptographic codes that, for now, are secure against most attackers. These codes rely not on absolute laws of nature, but on mathematics, complex equations so difficult that it would take today's supercomputers centuries to crack. Yet here lies the danger. Difficult does not mean impossible. With enough time, power, or a breakthrough in computing, any code can be broken. Already, we see cyber attacks escalating in sophistication. Entire governments, economies, and infrastructures are vulnerable to those who can slip through digital defenses. It is no exaggeration to say that the classical internet is, at its core, a network built on trust in mathematical difficulty rather than in vulnerability. But mathematics is a human construct, and sooner or later, human ingenuity, or worse, human malice, finds a way to outwit it. The looming rise of quantum computers only intensifies this problem. Classical cryptography depends on the assumption that factoring large numbers or solving certain problems will take impractically long. But quantum computers, harnessing the bizarre parallelism of qubits, threaten to solve these problems in hours or minutes. When that day comes, much of the encryption protecting our data, our governments, and our financial systems will collapse like a house of cards. In this light, the classical internet begins to look less like a miracle and more like a vulnerable bridge, one strong enough for today's travelers, but already trembling under the weight of tomorrow's demands. Consider also the issue of reliability. Classical signals degrade over distance, light pulses traveling through fiber optic cables scatter, weaken, and eventually require amplification. Electrical signals distort. Wireless transmissions are absorbed, blocked, or interfered with. To compensate, engineers build repeaters, routers, and error correction systems, but none of these are perfect. Each step along the chain is a chance for loss, delay, or interception. The result is a network that, while astonishingly effective, is never flawless. Lag, outages, breaches, and bottlenecks remind us constantly that we are still tethered to the imperfections of classical physics. Then there is the matter of scale. The internet we know is vast, but its architecture is patchwork. Billions of devices are connected, yet the pathways linking them are uneven. Urban areas enjoy blazing fast fiber, while rural regions struggle with slow connections or none at all. Satellites attempt to bridge the gap, but they too rely on classical transmission and are subject to weather, interference, and bandwidth limits. The dream of universal connectivity remains unfulfilled, constrained by the limits of our tools. And beyond the technical lies something deeper, something almost philosophical. The classical internet is linear, sequential, bound by time and space. When you send a message across the world, it must travel across undersea cables, bounce off satellites, route through data centers. It is fast, yes, but never instantaneous. Distance still matters, latency still exists. In this way, the internet reflects our classical intuition of the world. That information, like matter, must travel through space and time to reach its destination. But the universe, as quantum mechanics teaches us, is not bound by such linearity. Reality itself contains loopholes, shortcuts, and entanglements that transcend classical boundaries. The internet we know today is magnificent, but it is not cosmic. It is a human invention constrained by human imagination, still operating within the narrow rules of Newton and Maxwell, rather than the stranger, more powerful truths of quantum mechanics. These limits are not simply inconveniences. They shape the very way societies function. Governments pour billions into cybersecurity because the internet can be hacked. Businesses lose fortunes today to breaches because encryption is vulnerable. Scientists struggle to share massive datasets across continents because bandwidth is finite. Hospitals rely on digital records that can be intercepted or corrupted. Even our daily lives, our conversations, our identities, our financial stability depend on a system that is powerful but ultimately breakable. The stakes could not be higher, and yet we must not forget that these constraints are not failures but reminders. They remind us that human progress never ends. Just as the telegraph gave way to the telephone, and the telephone gave way to the internet, so too must the internet evolve. The classical network, for all its brilliance, has carried us as far as it can go. To move forward, we must embrace a new foundation, one built not on the approximations of classical physics, but on the unbreakable universe, deep laws of quantum mechanics. But before that leap, let us reflect once more on the scale of what we are asking from this network. We ask it to connect billions of minds in real time, to carry the weight of our economies, to secure our governments, to hold our most intimate secrets, to entertain us, to educate us, to guide us. We ask it to compress the vastness of human civilization into streams of binary code, flowing at nearly the speed of light without faltering. That it has managed to do so for decades is a triumph beyond measure. But the cracks are showing. Every cyber attack, every data leak, every moment of lag is a whisper of truth. This system, as mighty as it is not infinite. And so, the limits of the classical internet are not barriers to despair over, but thresholds inviting us to dream bigger. They are the universe telling us, you have gone far, but not far enough. You have built wires and waves, but nature offers you something deeper. You have relied on probability and difficulty, but the cosmos offers certainty and invulnerability in the form of entanglement. The classical internet has given us a global village. The quantum internet promises us a universal civilization. Thus, when we speak of the entangled future, we are not rejecting the marvels of the present. We are honoring them by daring to transcend them. We are acknowledging the limits of the classical internet, not to diminish its glory, but to recognize that humanity is ready to outgrow its childhood network and step into something far greater, something written not by human engineers alone, but by the laws of the universe itself. The classical internet has brought us here. The quantum internet will take us beyond. At the center of the quantum internet lies a mystery so profound that it reshaped our understanding of reality itself, quantum entanglement. To speak of it is to enter a realm where common sense falters, where the rules of everyday life collapse, and where nature reveals a hidden architecture stranger than dreams. This phenomenon, once dismissed even by Einstein as spooky action at a distance, is now the beating heart of an impending technological revolution. To grasp why the quantum internet has universe-changing potential, one must first grasp the astonishing implications of entanglement, not just as a scientific curiosity, but as a tool, a bridge, and a key to a new era of communication. Imagine two particles, photons of light, electrons, atoms, born together in a single interaction, like twins emerging from the same event. Quantum mechanics tells us that their properties, such as spin, polarization, or momentum, become linked, entangled in ways that defy ordinary logic. Measure one, and you instantly know the state of the other, no matter how far apart they may be. Separate them by a millimeter, a kilometer, or the distance between Earth and the Moon, and the link endures. It is as if reality itself maintains a thread between them, invisible yet unbreakable, transcending the normal limits of space and time. For centuries, humans thought information could only move like objects, pushed, pulled, transmitted through space. Entanglement smashes this view. In the quantum world, correlation is not constrained by distance. If one particle turns left, the other turns right instantly, as if the universe itself coordinates their dance outside the theater of classical physics. This is not mere speculation. It has been tested, confirmed, and measured in laboratories around the world. Entangled particles have been created and separated across cities, and even between Earth and satellites in orbit, proving that this strange bond is real and usable. But why does this matter for the internet? Because the internet is ultimately about one thing: sharing information. In the classical model, information must travel, a signal sent, a cable carrying, a satellite bouncing. Distance, interference, and interception always loom as obstacles. Entanglement offers a radically different paradigm. Information does not need to travel in the same way. By preparing entangled particles, one can create correlations between two distant points instantly. This opens the door to communication systems so secure, so efficient, and so resistant to eavesdropping that they could redefine what trust means in a connected world. Consider security, the lifeblood of digital society. In classical communication, no matter how strong the encryption, there is always the risk of interception. A hacker could copy your message while it moves through a wire or bounces off a satellite. But in a quantum, entangled system, the very attempt to measure or intercept the entangled particles destroys their state. The eavesdropper cannot observe without leaving a trace. It is as if the universe itself acts as a guard, warning both sender and receiver that their line has been compromised. For the first time in history, physics, not mathematics, not human effort, but the laws of reality itself, can guarantee absolute secrecy. This principle has already leaped from theory to practice. Quantum key distribution using entangled photons has been demonstrated across cities and from ground stations to satellites. In 2017, China's Michus satellite transmitted entangled particles over more than 1,000 kilometers, creating secure communication between distant points on Earth. What was once an eerie prediction is now an engineering milestone. These experiments show that entanglement is not merely a quirk of physics, but a resource, like electricity or magnetism, that can be harnessed, scaled, and built into the very fabric of a new internet. And yet, entanglement's promise extends beyond security. It is the foundation for linking quantum computers into networks. A single quantum computer is already powerful, capable of solving problems unimaginable for classical machines. But entangled connections could bind many such computers into a vast web, where quantum states can be shared, manipulated, and synchronized across the globe. In this vision, the quantum internet becomes not just a secure communication channel, but the nervous system of a planetary scale quantum computer. Imagine researchers across continents pooling their quantum resources as seamlessly as we now share documents in the cloud. Imagine solving simulations of molecules for drug discovery, or modeling climate systems, or even probing the structure of spacetime itself, all by weaving together entangled computers into a single, unimaginable mind. There is a deeper beauty here. Entanglement does not respect the boundaries we humans impose, boundaries of geography, distance, or separation. It whispers a truth that philosophers and poets have long suspected, that everything is connected in ways we cannot see. In using entanglement to build a new internet, we are not inventing connection, we are revealing the connection that already exists at the foundations of reality. Each entangled photon is a reminder that the universe is not a collection of isolated parts, but a tapestry, woven so tightly that pulling one thread tugs on another across space. The quantum internet will be more than a technological tool, it will be a philosophical revelation embodied in fiber, photons, and algorithms. Of course, entanglement is not without challenges. Quantum states are fragile, collapsing when disturbed by their environment. Entangled photons can be scattered, absorbed, or disrupted as they travel. Scientists must invent ingenious methods, quantum repeaters, error correction, advanced detectors, to preserve entanglement across long distances. This is no small task. Classical networks can simply boost a signal, quantum ones cannot, for copying a quantum state destroys it. Progress will demand entirely new kinds of infrastructure, new mathematics, and new engineering paradigms. Yet already progress is relentless. Laboratories across the world are demonstrating entanglement across increasing distances between more particles with greater reliability. The fragility of entanglement, once seen as an obstacle, is becoming a frontier for innovation. Entanglement also reshapes our sense of communication itself. In the classical world, communication is about transmission. I send, you receive. In the quantum world, it becomes about correlation. We share a state, and through it, we share information. It is less like passing a letter and more like tuning into the same frequency of the cosmos. This is a profound shift, for it suggests that future communication may not be bound by the metaphors of couriers and pipelines, but by harmony, resonance, and synchronization. The quantum internet will not simply carry messages, it will align realities, and think of the implications beyond Earth. As humanity dreams of colonizing Mars, exploring moons, or sending probes to distant stars, classical communication becomes strained. Signals to Mars can take minutes, to the outer planets hours, to the nearest stars years. Entanglement cannot transmit information faster than light in a classical sense, but it can establish correlations instantly across any distance. A quantum internet could create a framework where distant colonies remain entangled with Earth, ensuring security, coordination, and shared quantum resources across the solar system. It will not erase distance entirely, but it will offer tools no other form of communication can match. Some will ask, if entanglement is so powerful, why does it not allow faster than light messaging? The answer lies in the subtlety of quantum mechanics. While entanglement creates instant correlations, it does not transmit usable information without classical signals. Still, this does not diminish its utility, it enhances it. It means entanglement is not magic, not a violation of relativity, but a gift of nature that works within its laws. It is not about breaking the rules, it is about using the deeper rules that govern reality. In this sense, entanglement is both mysterious and trustworthy, a paradoxical but perfect foundation for a new internet. To see entanglement not as a curiosity but as a revolution requires imagination. Just as electricity was once a laboratory trick with no clear purpose, so too was entanglement once a strange puzzle in physics textbooks, but electricity gave us light, power, and civilization itself. Entanglement promises no less. In a few decades, we may look back at this time and marvel that we once sent messages using vulnerable pulses of light, unprotected by nature's own encryption. We may wonder how we ever accepted an internet built on distance, delay, and fragility, when the universe had already written into its fabric a better way. The heart of the revolution is not in machines, cables, or protocols. It is in entanglement itself. It is the realization that we can take the universe's strangest property and turn it into the most practical of tools. It is the courage to look at what Einstein doubted, what philosophers debated, and say, this is not just mystery, it is destiny. The quantum internet is not merely about connecting computers or people, it is about aligning our technology with the true nature of reality. Entanglement is not spooky, it is the future. And so, as we look ahead to an internet woven not of classical signals but of quantum threads, let us remember the wonder at its core. Entanglement reminds us that distance is less rigid than we think, that security can be absolute, that information can be shared in ways beyond transmission. It teaches us that the universe itself is a communicator, a network already humming with silent correlations, waiting for us to listen. The quantum internet will not invent this harmony, it will join it. And in doing so, it will change not only how we connect, but who we are, for to live in an entangled future is to live in recognition of our deepest truth, that we are, and have always been, inseparably connected. For as long as human beings have shared knowledge, there has been the fear that someone, somewhere, might intercept it. From the moment a message was carved into stone or whispered in a darkened room, others have sought to steal, decode, or corrupt the secrets of communication. Ancient kings devised codes, generals employed ciphers, spies carried hidden messages, and mathematicians spent lifetimes designing complex systems of encryption. Every age has believed its methods secure, and every age has eventually been proven wrong. The history of secrecy is the history of breaking it, but today, on the edge of the quantum frontier, we are promised something entirely new, communication guarded not by the cleverness of human design, not by the difficulty of mathematical puzzles, but by the inviolable laws of nature itself. This is the promise of the quantum internet, a world where communication becomes unhackable, where secrecy is no longer a fragile human construct but a cosmic guarantee. To appreciate the magnitude of this shift, one must first understand how fragile our current systems really are. Every time you type a password, make an online purchase, or send a private message, your data is protected by encryption, mathematical codes that scramble information into unreadable strings. These codes rely on problems so difficult that they would take classical computers centuries to solve. A hacker cannot simply guess your password or brute force their way through billions of possibilities, not quickly enough, at least. The assumption of security is built on the assumption of difficulty. But difficulty is not the same as impossibility. What is difficult for one generation of machines becomes trivial for the next. Codes thought unbreakable in the 1940s now look like child's play, and looming on the horizon is the most dangerous codebreaker of all, the quantum computer. Quantum computers, unlike their classical counterparts, do not evaluate problems step by step. Their qubits can exist in superpositions, exploring multiple possibilities simultaneously. Algorithms already exist, such as Shor's algorithm, that, when run on a sufficiently powerful quantum machine, could crack widely used encryption schemes in minutes or seconds. This means that the bedrock of internet security, the algorithms protecting banks, militaries, hospitals, and governments, could crumble almost overnight. Imagine the chaos if every locked door on the internet suddenly swung open, every financial transaction visible, every state secret exposed, every private message revealed. This is not science fiction. It is a ticking clock, one that scientists and policymakers are acutely aware of. Enter the quantum internet armed with the extraordinary weapon of entanglement. Unlike classical encryption, which relies on mathematical difficulty, quantum communication relies on physics itself. At its heart lies a principle known as the no-cloning theorem, which states that quantum information cannot be copied without altering it. Combine this with entanglement, and you have a system in which the very act of eavesdropping becomes impossible to hide. If a hacker tries to intercept or measure an entangled particle carrying information, the particle's state collapses and both sender and receiver are immediately aware of the intrusion. It is as if the locks of your digital home are not just strong but self-aware, able to detect the moment someone touches them and instantly alert you. This leads us to quantum key distribution QKD, the practical foundation of secure quantum communication. In QKD, two parties, traditionally called Alice and Bob, share entangled particles. By measuring their respective particles, they generate a shared secret key, a sequence of bits that is identical on both ends. This key is then used to encrypt classical messages. The beauty lies in the fact that if an eavesdropper, Eve, tries to intercept, her interference introduces errors that Alice and Bob can detect. If too many errors appear, they know the line is compromised and discard the key. If the line is clean, they proceed, confident that no one has listened in, unlike classical cryptography, where one can never be entirely certain that a code is unbroken. Quantum cryptography provides certainty. Security is no longer a matter of trust, it is a matter of physics. Already, nations and corporations are racing to build quantum, secure networks. In 2017, scientists used China's MISHA satellite to establish a secure quantum link between Beijing and Vienna, spanning thousands of kilometers. Banks in Switzerland have tested QKD for protecting financial transactions. The European Union and the United States are pouring resources into quantum communication infrastructure. These are not theoretical games, they are the early bricks of a new wall of security, one built not on shifting sand but on the bedrock of quantum law. The implications stretch far beyond technical security. In a world where cyberwarfare is a daily threat, where critical infrastructure from power grids to hospitals can be paralyzed by hackers, the ability to guarantee unbreakable communication is a matter of survival. Governments spend billions defending against cyber attacks, yet every defense today has cracks. With quantum communication, leaders could exchange commands knowing they cannot be intercepted. Armies could coordinate without fear of espionage. Businesses could negotiate deals, scientists could share sensitive data, journalists could protect their sources, all with the confidence that their words are heard only by those intended. In such a world, trust is no longer fragile. It is guaranteed. Yet the significance is not merely practical, it is also philosophical. For centuries, secrecy has been an illusion. Every lock has a key, every wall a weakness, every code a flaw waiting to be discovered. Humanity has lived in a state of uneasy faith, hoping that our secrets are safe but never knowing for sure. The quantum internet changes this dynamic forever. It introduces, for the first time, the possibility of absolute privacy. To communicate securely is no longer to gamble on the slowness of your adversary, but to rest in the certainty of natural law. This is a profound transformation, not just of technology, but of human confidence. It shifts our relationship with information from fear to assurance. Of course, challenges remain. Building large-scale quantum networks is immensely difficult. Entangled particles are delicate, easily disturbed by noise or loss in transmission. Maintaining entanglement across cities, let alone continents, requires quantum repeaters and advanced engineering. The equipment is still expensive, bulky, and confined to research labs. Skeptics argue that practical global-scale quantum communication is decades away. But history teaches us that today's impossibilities often become tomorrow's necessities. The internet itself once seemed unfeasible, its infrastructure too costly, its purpose unclear. Yet today, it is the backbone of civilization. The same destiny awaits quantum communication. The stakes are simply too high for it not to succeed. As we contemplate this unhackable future, one might wonder, will this technology be used for good or ill? Security can protect, but it can also conceal. Governments could use quantum secrecy to hide abuses of power. Criminals could employ unbreakable codes for illicit purposes. Like every tool in history, the quantum internet carries both promise and peril. Yet the balance of its potential leans overwhelmingly toward progress. Just as the printing press was used both for propaganda and for enlightenment, just as the internet has been used for deception and for truth, so too will quantum communication become what humanity makes of it. The difference is that, for the first time, the foundation will be unshakable. The question will not be whether messages can be intercepted, but whether they should be sent. Imagine, then, the world that could emerge. Hospitals exchanging patient data without fear of leaks. Financial institutions moving trillions of dollars across borders without risk of theft. Scientists collaborating on sensitive projects without industrial espionage. Families speaking privately across oceans, secure in the knowledge that no one else is listening. In such a world, the basic human right to privacy, so often compromised in the digital age, could finally be restored. The internet, once a place of both wonder and danger, could become a realm of trust. And beyond Earth, as humanity stretches into the stars, this security will be even more critical. Communication with space colonies, orbital stations, or interplanetary probes must be protected from interference. Classical signals can be jammed, intercepted, or falsified. Quantum communication, by contrast, ensures that information remains pure, uncorrupted, untouchable. As we expand into the cosmos, building a civilization among the planets, the quantum internet may prove not just useful but indispensable, a cosmic immune system for the nervous system of our species. What makes this all the more extraordinary is that the guarantee of security does not come from human invention, but from the very fabric of reality. It is not an algorithm that might one day be broken, nor a wall that might one day be breached. It is the structure of the universe itself declaring, "You may share this message, and no one else may see it." The cosmos has offered us, in the fragile yet powerful phenomenon of entanglement, the gift of certainty. It is a gift we must learn to use wisely. So when we speak of the entangled future, we are not merely speaking of faster networks or novel gadgets. We are speaking of the dawn of unhackable communication, the end of the ancient cat and mouse game between code makers and code breakers. We are speaking of a future where secrecy is not a privilege of the powerful, but a birthright of all who communicate. We are speaking of an era in which humanity finally builds its digital world on the same unbreakable foundations that govern the stars. The classical internet has served us well, but its walls are thin, its locks fragile, its doors too easily forced. The quantum internet promises to build a citadel not of stone or steel, but of physics itself. Within its walls, our words, our identities, our dreams will be safe. Not because we are clever enough to hide them, but because the universe itself refuses to betray them. That is the revolution of unhackable communication. That is the promise of absolute security, and that is why the entangled future is not just desirable, it is inevitable. When people hear the phrase quantum internet, many imagine simply a faster version of what we already have: quicker downloads, smoother video calls, instantaneous searches. But that vision, while tempting, misses the true scale of the revolution. The quantum internet is not merely about moving data more efficiently, it is about linking together the most extraordinary machines humanity has ever conceived, quantum computers, into a single, entangled network of unimaginable capability. To understand this, one must recognize both the power of a quantum computer on its own and the exponential leap that occurs when such machines are joined through entanglement. This is not just faster computing, it is a new species of intelligence, a planetary mind whose potential dwarfs anything that classical machines can achieve. Classical computers, from the first vacuum tubes to the sleek devices in our pockets today, operate on tiny switches that are either on or off, represented as ones and zeros. The logic of everything digital, from the simplest calculator to the most powerful supercomputer, is built from these binary choices. But no matter how fast or numerous these bits become, they remain constrained. They evaluate problems step by step, sequence by sequence. Add more processors and you can solve more problems, but you are still trapped in the linear grind of classical logic. Quantum computers break this mold entirely. Their building blocks, qubits, are not limited to ones or zeros. Through the principle of superposition, a qubit can exist in a blend of states, both 1 and 0 at the same time, until measured. This strange behavior allows quantum computers to explore vast numbers of possibilities simultaneously. Where a classical computer might test one lock combination after another, a quantum computer can, in effect, test them all at once. Problems that would take classical machines billions of years can, for certain tasks, collapse into minutes under the power of quantum algorithms. Already, even the small quantum processors built today have shown tantalizing glimpses of this power. They have simulated molecules in ways classical computers cannot, optimized problems with countless variables, and demonstrated quantum supremacy. In specific tasks, achieving results no conventional machine could match, yet these are only the first steps. The real transformation will occur not when we have isolated quantum computers, but when we connect them. Imagine not a single quantum brain, but a network of them, entangled across continents, sharing qubits, states, and processing power as if distance were irrelevant. That is the promise of the quantum internet, not isolated islands of brilliance, but a global ocean of intelligence. The synergy here is staggering. In the classical world, connecting computers gives us the internet, a network of machines exchanging data. But in the quantum world, connecting computers through entanglement does more than exchange, it fuses. Entangled qubits in different locations behave as parts of the same system. Linking quantum computers in this way could allow them to perform joint computations, share quantum states, and distribute workloads in ways impossible for classical machines. It would not be a network in the sense we know today. It would be a collective quantum machine, a global brain with nodes spread across the Earth. To glimpse the scale of this, consider just one field, drug discovery. Designing a new medicine requires simulating how molecules interact, a task so complex that even the most powerful supercomputers struggle. The number of possible configurations of a single protein can exceed the number of atoms in the universe. A single quantum computer can already model some of these structures with unprecedented accuracy, but a network of quantum computers, entangled and working in harmony, could tackle the full complexity of biology, unveiling cures and treatments at a pace never before imagined. Diseases that today seem intractable, cancer, Alzheimer's, viral pandemics, could be understood and conquered through the insights of an entangled quantum network. Or consider climate modeling. Our planet's atmosphere, oceans, and ecosystems form an interconnected system of staggering complexity. Classical models approximate, simplify, and predict with varying degrees of accuracy, but they are always limited by computational power. A global quantum internet, pooling the abilities of entangled machines, could simulate Earth's climate with breathtaking precision, allowing humanity to foresee disasters, plan responses, and perhaps even reverse environmental damage. The fight against climate change, which often feels like a battle against uncertainty, could shift decisively in humanity's favor. The implications extend into realms even more profound. Quantum networks could simulate the very fabric of the universe, modeling interactions at the scale of subatomic particles or entire galaxies. They could explore questions classical physics cannot answer, test hypotheses about dark matter or quantum gravity, and probe the boundary between the known and the unknown. With each entangled connection, humanity gains not just more power but more vision, more ability to ask and answer the deepest questions of existence. This vision is not without challenges. Entangling quantum computers requires delicate infrastructure. Qubits are notoriously fragile, collapsing into classical states when disturbed by their environment. Maintaining entanglement across networks demands innovations like quantum repeaters, error correction protocols, and ultra-cooled environments. These are formidable engineering challenges, but progress is relentless. Already, researchers have demonstrated quantum teleportation of information between distant nodes, entanglement between separate labs, and small-scale quantum networks that hint at what is to come. The road is long, but the direction is clear. One might ask, why do we need to link quantum computers? Why not simply build larger, more powerful ones? The answer lies in scalability and resilience. A single quantum computer, no matter how advanced, remains limited by the number of qubits it can house and control. Linking machines allows for modular growth, distributing complexity across a network. It is the same principle that made the classical internet so transformative. No single computer, no matter how powerful, could match the collective intelligence of billions working together. The quantum internet applies this lesson at a higher order, creating not just collaboration but entanglement, a form of unity more profound than anything classical machines can achieve. There is also the matter of democratization. Just as cloud computing allows individuals and companies to rent processing power from remote servers, a quantum internet could allow anyone to access quantum resources from anywhere. You might sit at a laptop and, through the entangled web, tap into the power of vast quantum machines distributed across the globe. This could open the door to innovation not just in elite laboratories, but in classrooms, startups, and developing nations. The quantum internet could democratize access to the universe's most powerful computational resource, unleashing creativity and discovery on a planetary scale. And what of artificial intelligence? Already, AI shapes our lives, from search engines to medical diagnostics to self self-driving cars. But classical AI, for all its advances, is still bound by classical computation. Imagine linking AI systems to a quantum internet, giving them access to quantum, enhanced learning, optimization, and reasoning. The result could be artificial minds capable of insights and decisions far beyond current limits. Used wisely, such systems could accelerate progress in science, technology, and society. Used recklessly, they could pose challenges we must confront with care. The quantum internet will not only magnify our capabilities, it will magnify our responsibilities. In contemplating such power, one cannot ignore the ethical dimension. Who will control this global quantum brain? Will access be equitable, or will it deepen divides between nations and classes? Will it be used to solve humanity's greatest problems, or to wage more sophisticated wars? The internet itself, once heralded as a tool of freedom, has also become a tool of surveillance, manipulation, and division. The quantum internet could follow the same path unless we learn from history and build it with wisdom. The stakes are higher than ever, for the intelligence it unleashes will not merely process data, it will shape civilization itself. Yet, despite these concerns, the potential is too vast to ignore. Linking quantum computers through entanglement is not a choice humanity can avoid, it is a destiny written into the trajectory of science. Every step in human progress, from language to electricity to computation, has been a step toward greater connection, greater power, greater understanding. The quantum internet is simply the next step, a leap into a realm where the boundaries of distance, scale, and complexity dissolve. It is the unfolding of what was always implicit in the fabric of reality, that intelligence, like entanglement itself, is meant to be shared. And so, as we envision this entangled web of infinite power, let us not be afraid of its enormity. Let us instead recognize it as the natural continuation of humanity's quest to know, to connect, to transcend limits. A single quantum computer is a marvel, a network of them is a miracle. Together, they will not only solve the unsolvable, they will redefine what it means to think, to know, and to be human in an interconnected universe. The classical internet gave us a global village. The quantum internet, linking quantum minds, will give us something greater still, a universal civilization of intelligence, woven together by the deepest threads of reality. When we speak of the quantum internet, we usually describe it in terms of physics, engineering, and technology, entanglement, qubits, photons, repeaters, and protocols. But beneath the wires, the mathematics, and the laboratories, there is something far deeper stirring, something that transcends circuits and code. The quantum internet challenges not only our technical imagination, but also our philosophical understanding of existence itself. It asks us to reconsider the nature of reality, the boundaries between individuals, and the meaning of connection in a universe where separation is, perhaps, only an illusion. To explore the philosophical implications of this technology is to stand at the edge of both science and spirit, peering into a mirror the universe is holding up to us through the very act of entanglement. At the heart of quantum mechanics lies the strange and profound phenomenon of entanglement. When two particles become entangled, their states intertwine in such a way that they are no longer independent. Measure one and you instantly know the other, no matter how far apart they are. Einstein called it spooky action at a distance, as if the universe were mocking our classical intuitions about separation. For centuries, we have believed in locality, in the idea that objects here cannot be influenced by objects there without something traveling between them. Yet entanglement suggests otherwise. It suggests that at some deep level the universe is whole, and that parts we thought were separate are in fact aspects of a unified reality. The quantum internet takes this phenomenon from the abstract realm of theory into the tangible fabric of society. To build such a network, we are not merely sending signals, we are creating entanglement between distant nodes. That means that in some sense our communication infrastructure will no longer be about transmitting information across space, but about revealing connections that already exist beneath the surface. Philosophically, this is astonishing. It implies that what we call distance may be less fundamental than connection, that our division into here and there, mine and yours, may be a convenient fiction, not an ultimate truth. This has profound implications for how we see ourselves as individuals and as a species. For centuries, human philosophy has wrestled with the tension between separateness and unity. We live as separate beings, distinct bodies, distinct minds, distinct lives. Yet we also sense a deeper connection, in love, in empathy, in the recognition of shared humanity, and in the patterns of nature that bind us to the stars. The quantum internet embodies this paradox in a literal, physical form. It tells us that even the most precise scientific instruments reveal a universe where separation is secondary and interconnection is primary. Consider what it means for communication itself. In the classical sense, to communicate is to send something from one place to another, to bridge a gap between two minds. But in the quantum sense, communication becomes an act of uncovering entanglement, of realizing that two minds, two machines, two nodes are already part of a shared system. If this metaphor extends, then perhaps all human communication is less about crossing a void and more about awakening to a unity that was always there. The quantum internet, then, does not merely transmit information, it embodies a truth about being, that knowledge, meaning, and connection are woven into the fabric of reality itself. There is also a spiritual echo here. Many ancient philosophies and spiritual traditions have long spoken of the interconnectedness of all things. The Taoist speaks of the Tao, the underlying flow that binds everything. The Hindu speaks of Brahman, the ultimate reality of which all beings are expressions. The Buddhist speaks of interdependence, that nothing exists in isolation, that all phenomena are empty of independent selfhood. Even in Western traditions, the mystical currents of thought often stress unity, that creation is one, that love is the bond that transcends time and space. For millennia, these ideas were matters of faith or intuition. Now, through the quantum internet, we see science building technology on a principle that echoes these ancient insights. This convergence is not to be taken lightly. It forces us to ask, is entanglement merely a useful trick of mathematics, or is it a revelation of something deeper? When we create an entangled network, are we not, in some way, participating in the universe's own interconnectedness, making it visible, tangible, and practical? The quantum internet becomes not only a tool of computation and security, but a symbol of unity, a reminder that the divisions we perceive are, perhaps, only surface appearances. The philosophical implications extend to our notions of identity and individuality. In the classical world, a computer is itself, distinct from other computers, interacting by sending messages across wires. In the quantum world, two computers entangled are no longer fully separate. They form part of one extended quantum system. This raises the question, when humans are deeply connected, emotionally, socially, spiritually, are we too part of one extended system? Is individuality absolute, or is it, like classical separateness, an emergent illusion masking a deeper unity? The quantum internet gives us a new lens through which to ask these questions, not in abstract speculation, but through a physical reality we are actively constructing. Furthermore, entanglement challenges our sense of causality and time. If two entangled particles correlate instantly across vast distances, what does this mean for our linear notions of before and after, cause and effect? If information is secured not by traveling through space but by shared entangled states, are we glimpsing a reality where time and space are not fundamental scaffolds but emergent properties? The quantum internet forces us to confront these questions not as thought experiments, but as engineering puzzles. And every time we solve one, we are also probing the foundations of existence. There is a moral dimension as well. If the quantum internet symbolizes a reality where all things are interconnected, then perhaps our ethical frameworks must expand to reflect this truth. The illusion of separateness has often justified exploitation of nature, of other people, of future generations. But if at the most fundamental level we are entangled, then harming others is, in a sense, harming ourselves. The quantum internet could thus serve as both metaphor and reminder. We are not isolated actors in a void, but participants in a web of being where responsibility and compassion are inseparable from truth. Imagine a child, years from now, learning not just that the internet exists, but that it is quantum, that their messages, their learning, their interactions are carried on threads of entanglement. What philosophical outlook might this inspire? Perhaps they will grow up less prone to see themselves as separate, less inclined to define progress as domination, and more able to see connection as the core of reality. The technologies we build are not neutral, they shape our consciousness. Just as the classical internet reshaped how humanity thinks about knowledge, identity, and community, so too will the quantum internet reshape how we think about reality itself. Yet there is a cautionary note here. The same interconnectedness that inspires awe can also inspire fear. If all things are connected, then nothing is fully private, nothing is fully independent. The quantum internet, with its unhackable security, may reassure us that our data is safe, but the philosophy of entanglement whispers something more unsettling, that the walls we erect between self and other may be more fragile than we wish to believe. To live in an interconnected universe is to accept vulnerability, to accept that we are not sovereign islands but interwoven threads. For some, this is liberation, for others it is loss. The quantum internet will force us to wrestle with this tension, not in theory but in practice. And then there is the cosmic scale. If entanglement connects particles across galaxies, if the universe itself is threaded with these invisible bonds, then the quantum internet is not just a human invention, but a participation in the universe's own nature. We are not creating something artificial, we are uncovering what was already there, aligning our technology with the architecture of reality. This raises the most profound philosophical question of all. What does it mean to live in a universe where connection is fundamental? Perhaps it means that our search for meaning, our longing for unity, our impulse to communicate and create, are not accidents of biology but reflections of the cosmos itself. The quantum internet, then, is not just a tool. It is a teacher. It shows us that the future of communication, of computing, of society, rests not on faster isolation but on deeper connection. It challenges the myth of separateness that has guided much of human history and invites us into a story where we are, at root, entangled. And if we can accept this, if we can live into the truth that the universe itself is a network of relationships, then perhaps we will find new ways of being human, ways marked less by division and more by unity, less by fear of the other and more by recognition of the self in all. The philosophical implications of the quantum internet are therefore not side effects but central truths. To build it is to embody the lesson that everything is connected. To use it is to participate in a web that mirrors the universe. And to reflect on it is to be reminded that our deepest task as a species is not merely to invent technologies, but to understand what they reveal about who we are and what reality is. In Entanglement, we glimpse the universe whispering its secret, that separation is illusion and connection is truth. The quantum internet will carry not only information but revelation, the revelation that the future is not about building walls of speed and power, but about uncovering the threads that bind us into one entangled whole. When we talk about the quantum internet and the universe-changing potential it holds, it is easy to let our imagination soar to the highest visions, unhackable communications, networks of entangled quantum computers, a civilization woven together by threads of physics itself. Yet, as with every transformative leap in human history, the path from dream to reality is neither simple nor smooth. It is filled with obstacles, technical, economic, philosophical, and political. To acknowledge these challenges is not to dampen the vision but to respect its enormity. For every dawn of a new era is preceded by a long night of effort, confusion, and trial. The quantum internet is no different. What we see now are only the first rays of light at the horizon, promising but fragile, demanding persistence, courage, and humility. The first challenge lies in the fragility of the very thing that makes this revolution possible. The qubit, a classical bit, is robust. It can be a 1 or a 0 with clarity and permanence. A qubit, by contrast, is delicate almost beyond comprehension. It exists in superposition, a blend of possibilities, but this state is easily disturbed by the tiniest interaction with its environment. Heat, vibration, electromagnetic noise, even a stray atomany of these can collapse a qubit into a definite state, destroying the quantum information it carries. This fragility is the greatest enemy of the quantum internet. To create stable entangled links across vast distances, we must learn to tame a phenomenon that is, by nature, ephemeral. Researchers have devised ingenious solutions. They cool qubits to near absolute zero, shielding them from noise. They encode information redundantly, creating quantum error correction schemes that can preserve data even as individual qubits fail. They experiment with photons, which can travel long distances through fiber optic cables, and with quantum repeaters, devices that can extend entanglement step by step. Each breakthrough brings us closer, but the road is long. Unlike the classical internet, where electrical signals can race across copper wires with little resistance, the quantum internet must contend with a reality where distance and noise erode coherence at every turn. It is like trying to carry a candle through a storm. The flame wants to go out at every step. Beyond physics, there is the challenge of scale. A laboratory demonstration of quantum teleportation between 2 points a few kilometers apart is impressive, but it is far from a global network. To build a quantum internet spanning nations, continents, and eventually the planet, we must scale these experiments by orders of magnitude. This requires infrastructure, specialized fiber optic cables, satellites that can entangle photons across space, nodes that can generate and manage qubits with precision. Such infrastructure will demand immense investment, not only in money but in cooperation. No single laboratory, company, or even nation can build the quantum internet alone. It must be a collective project, a global undertaking. And as history shows, cooperation at such scales is always fraught with politics, competition, and mistrust. Then there is the challenge of talent and knowledge. Quantum science is not merely an extension of classical science. It is a different paradigm with its own mathematics, intuitions, and mysteries. To train a generation of scientists, engineers, and thinkers who can build and sustain the quantum internet is itself a monumental task. Universities must adapt curricula, industries must invest in education, and governments must support research with patience and vision. In an age when funding often chases short-term returns, sustaining the slow, uncertain progress of quantum technology is a challenge in itself. Without vision, we risk abandoning the effort just as its true potential is within reach. The dawn of a new era also brings the challenge of ethics and power. The classical internet was born with the promise of openness, democratization, and freedom, yet it also became a tool of surveillance, manipulation, inequality, and control. Will the quantum internet repeat this pattern, but on a grander scale? An unhackable communication system could be a shield for privacy, or a fortress for those who wish to operate in secrecy. A network of quantum computers could empower breakthroughs in medicine and science, or concentrate unimaginable power in the hands of a few. The dawn of this era forces us to ask, who will own the quantum internet? Who will control access to its resources? Will it be built as a commons for humanity or as a weapon for the powerful? These are not technical questions. They are questions of values, governance, and humanity's moral compass. At the same time, we face the challenge of imagination. The classical internet transformed the world in ways no one predicted: social media, streaming, e-commerce, the gig economy, virtual communities. The quantum internet, too, will unleash possibilities we cannot yet foresee, but this is a double-edged sword. Surprises can liberate, but they can also destabilize. We must cultivate not only the science to build the quantum internet, but the wisdom to imagine its consequences. How will education change when quantum resources are available globally? How will warfare change when communication is absolutely secure? How will economies adapt when optimization problems once deemed impossible become solvable in seconds? The dawn of a new era is always accompanied by uncertainty, yet amid all these challenges the horizon glows with promise. The dawn is real. Already, quantum key distribution has been demonstrated, sending encrypted messages secured by the laws of physics themselves. Already, satellites have transmitted entangled photons across hundreds of kilometers, proving that global quantum links are possible. Already, small quantum networks have been built, showing that entangled communication between distant nodes is not science fiction but science fact. Each of these achievements is like the first telegraph wire, the first radio signal, the first packet of data sent across ARPANET. They are humble beginnings, but history teaches us that humble beginnings often lead to revolutions. The dawn of the quantum internet is also the dawn of a new human perspective. Just as the classical internet reshaped how humanity views knowledge and community, the quantum internet will reshape how we view reality itself. It will embed in our daily lives the truth that entanglement is real, that connection is fundamental, that separation is not the whole story. To live in a world where your communication is secured by quantum entanglement is to live in a world where the philosophy of unity is no longer abstract but practical. The dawn is not only technological, it is existential. Of course, dawns are delicate. The first light of day can be obscured by clouds, delayed by storms, or forgotten in the weariness of night. The quantum internet will not arrive all at once in a blaze of glory. It will creep forward through incremental advances, each one fragile, each one demanding care. It may stumble, suffer setbacks, even collapse in places before rising again. But dawns, once begun, cannot be undone. The sun will rise, and the quantum internet, once envisioned, will eventually come into being. The only question is how, and what kind of world we will shape with it. This is why the challenges matter. They are not obstacles meant to discourage us, but tests meant to prepare us. To build the quantum internet is to confront not only the fragility of qubits, but the fragility of our own wisdom. It is to ask whether we can wield power without falling into domination, whether we can embrace unity without erasing individuality, whether we can step into a new era without repeating the mistakes of the past. The dawn will come, but what we see when the light fully breaks depends on how we meet these challenges now. In every era of human history, there has been a frontier that defined the future. Once it was fire, then it was agriculture, then it was the written word, electricity, industry, computation. Each frontier was both opportunity and trial. Each one carried the potential to elevate humanity or to entrench its flaws. The quantum internet is the frontier of our age. It will test us, stretch us, and define us. The challenges we face are immense, but so is the dawn they promise. And so, when we speak of the quantum internet's universe-changing potential, let us not imagine a future without struggle. Let us imagine a future born through struggle, forged in the crucible of fragile qubits, complex ethics, global cooperation, and human imagination. Let us imagine a dawn not given but earned, a dawn that reflects not only the genius of our science but the maturity of our species. If we can meet the challenges with courage, humility, and vision, then the dawn of the quantum internet will not just change our technology, it will change our understanding of ourselves, of reality, and of the universe we inhabit. The challenges are real, the dawn is certain, and what lies beyond that dawn is a future more entangled, more connected, and more extraordinary than we can yet conceive.